All right, welcome back to AP Physics 1, Unit 5, Linear Momentum. In the last video, we defined what momentum was. We looked at the equation. Now let's talk about impulse. Okay, so impulse, excuse me, right, is, so what we're going to do is remember that when we have an unbalanced force, it's going to accelerate the object, whether we speed it up or slow it down, which means if the object changes velocity, then the momentum is also going to change. Okay. Now, when a force is delivered to an object over a period of time, that object is going to experience an impulse. Okay. And so what we can actually do is, and we'll look at it in the impulse momentum theorem, but there's a relationship involving Newton's second law here, because you can see force, right? You can see time. We can do some simple substitutions, okay, to figure out and derive an expression. So the formula for impulse is J equals F delta T. Okay, now impulse and force are both vector quantities. Okay, so what we say is that the impulse is a vector that points in the same direction as the force exerted on the object, right? So if I'm looking at my golf club here, right, my force is along that line, which also means that my impulse will be in the same direction, right? They're both vectors. If I'm looking at the person being hit in the face, right, my force, right, well, just have to choose a different color for that one. There's a lot of dark there, right? Impulse, right? They all go along the same line. Same thing here with the hockey players, right? Force, right? Impulse, right? So they're going to point in the same direction. They're going to be along the same line. Okay. So if we want to look at some relationships, right? We know that J is going to be directly proportional to force. So if I want more impulse, I increase the force. J is also directly proportional to time. If I want more impulse, I increase delta T. But the most important kind of relationship that you can use in this equation is the fact that F is inversely proportional to 1 over delta T. Okay, this relationship is important because this is how we talk about car safety, helmet safety, is we want to kind of do something here. Okay, now graph-wise, okay, impulse is the area. All right, sorry, it's a bad area. Under a force versus time graph. Now, that's what you're going to see. When we get to the impulse momentum theorem, you're going to see a force versus time graph. In fact, I think it's an acceleration versus time graph, but we can turn it into a force versus time graph, right? And so this is where car crash data comes into play. Okay, so when we look at the area under that curve, we're able to figure out the impulse, which then allows us to figure out the change of momentum and so forth, right, to help us make informed decisions or help car manufacturers make informed decisions about airbags and different kinds of technology. All right, so let's look at an example problem. This is a very simple example problem. So you push on a 22 kilogram cart with a force of 6.5 newtons. If you push for 1.9 seconds, what is the magnitude of the impulse you deliver to the cart? So they provide extra information. You don't need the mass because, simply enough, impulse is J equals F delta T. So all we have to do here is multiply the force we're pushing with, right, with the time we're doing it in. So the impulse we give to the cart is 12.4 Newton seconds. Okay, and in fact, impulse kind of has two units. If we go back to our unit for momentum, Newton second is also a kilograms times meters per second. Because remember, a Newton is a kilogram times meters per second squared. right? And then I'm multiplying that by seconds. And then what happens? That S cancels 1 on S on the bottom, and we end up with our unit for momentum. All right? So in the next video, we're going to bring it together, right? So we talked about momentum, we talked about impulse, and now we're going to kind of put them together into something known as the impulse momentum theorem.